So for the Sticky Tape Labs summary page, the last two pages, pages 3 and 4, have those three problems on them. These are ways for us to start representing charges on objects, how they would look, how they would move around, and really kind of build upon our idea of objects having an excess charge, and that is why there is an electric force between them. On the two previous pages, we had that table where we identified the attraction, repulsion, or no interaction between materials, and drew force diagrams as appropriate. You would have concluded those two previous pages by identifying the charges on some of our materials. We said that that plastic rod that was rubbed with fur was assumed to be a negatively charged object. Because it was attracted to our top tape, and we know opposites attract, we were able to say that the top tape should be positively charged. And because the negatively charged plastic rod was repulsed by the bottom tape, or the bottom tape was repulsed by the plastic rod, that should be a negative charge. Like charges are repulsed, opposite charges are attracted. So we have our positively charged top tape and our negatively charged bottom tape. However, neither of these two tapes would have been attracted to anything if we hadn't separated them. So when we put these two things together, we had our top tape on top of our bottom tape, which was all on top of the table tape. But in this situation, these two things combined had an overall charge of 0. It wasn't until we had separated them that we were able to see the top tape and the bottom tape be attracted to each other and other things. What that means is the charge must have been transferred from one of these things to the other. We should know from chemistry that our atoms, the building blocks of the universe, consist of an inner nucleus, which consists of neutrons that have a neutral charge, as well as our protons, which have a positive charge. Surrounding the nucleus is going to be a cloud of negatively charged electrons. Now, typically in a balanced neutral system, the amount of positive charges we have are equal to the amount of negative charges we have. And then that negatively charged cloud is uniformly distributed. And then just to make it even easier, we typically won't even represent that nucleus. You'll typically be seeing it as our positive inside of a circle where we have an even distribution of our negative charge. However, if we have more positives than we have negatives, it's positively charged. If we have more negatives than we have positives, it will be negatively charged. Because our top tape ended up being positively charged, we would represent more positive charges on the top tape. And we would have more negative charges on the bottom tape. Now, realistically, we would probably want to be representing both the top tape and bottom tape having protons because the protons don't move, so they both have a positive charge. All we'd really be representing is that there'd be more of those negative charges or the electrons on the negatively charged bottom tape. But just to keep things simple, we'll have positives and negatives, and then that's just what we'll be representing here. So for problem 1, I am showing that we have our positive charges on the top tape, and we have our negative charges on the bottom tape. Those came from our overall neutral charge for the top and bottom tapes together. Problem 2, you're trying to invent a way for the paper to be attracted to both a top and a bottom tape while keeping these facts in mind. The paper is neutral. We did not do anything to induce a charge. And the electrons, those negatively charged particles, cannot move through the paper. Shown on the paper are 5 non-mobile atomic cores. Draw in the electron cloud for the 5 atoms in the paper. Now, we saw that our paper was weakly attracted to both the top tape and the bottom tape. That's why we're showing that it has a slight angle here towards both the top tape and the bottom tape. We're trying to represent what is going on here. We know that the top tape is going to be positively charged. We represented that in the previous problem. So we have a bunch of those positive charges here. And for the bottom tape, we said that that was going to be mostly negatively charged. We are told that our atomic cores consisting of that positive charge are non-mobile. They have to stay where they are. But we do need to show an attraction somehow. The fact that those cores cannot move, those circles representing our atomic cores, these will have to stay where they are. But what can change is the location of that negative charge. For example, for the piece of paper that's attracted to the top tape, we know it's attracted. The top tape is an excess of positive charge, so our negative charges are going to have to be closer to the top tape than our positive charges would be. That's how these things would be attracted. However, on our bottom tape, we can't move those positive charges because that's the core of the atom. But the distribution of the negative charge in the cloud, it can move away. So that way our positive charges from the core of our atoms are relatively closer to the negatively charged bottom tape. These two things are attracted to each other, which is why we are representing those as the closest. Over here, these are what's attracted to each other, and that is why they're going to be relatively close to one another. When we're inventing a way for the papers to be attracted to both, we need to keep in mind the fact that those positive charges can't move. And we're not really gaining or losing any charge because those negative charges can't go anywhere. They're not touching anything. But they can be moving their orientation in the atomic core, or at least the cloud around the core, to have that charge distributed around. This last one, instead of the paper, we're going to be focusing on the foil. Invent a way for the foil to be attracted to both a top and bottom tape while keeping these facts in mind. The foil is neutral. We did not do anything to induce a charge there. Each atom has a free electron that can move around. So in our paper, the electrons had to stay where they were. But in our foil, a metal, the electrons can freely move. Our top tape is still positively charged. Our bottom tape is still negatively charged. In order for the piece of foil to be strongly attracted to the top tape, we want those negative charges to be as close as possible to the positive charges. They're even outside of that atomic core, like in our paper, and they're way closer, which is how we could have a stronger attraction. For the piece of foil that's attracted to the bottom tape, that just means that the electrons, or those negative charges, need to be moved as far away as possible. So that way, what is closest to the negatively charged bottom tape will be the positively charged portion of the foil.